Okay, welcome to the last talk of this morning. Are we ready? Okay, it is my pleasure to introduce Juan Rivera-Letelier from University of Rochester, who will talk about, I don't know, it's a surprise.
Okay, thank you. Thank you, Luna, for the invitation to celebrate Carsten's work and birthday. So, all right, so I would like to discuss about nice quasidisks. And prime orbit counting. Okay, so these are some prime number theorem types for counting periodic points. And I want to start just mainly to fix notation. I want to remind you of the prime number theorem, so the classical prime number theorem. And for that, so this is about the prime counting function. That I'm going to denote by capital pi. And this simply counts the number of prime numbers that are less than or equal than x. All right, so the prime number theorem says that so it gives the asymptotics of this function. It says that this function grows like x over log x, in the sense that the quotient will converges to 1. So in other words, the number of prime numbers that are less than or equal than x is equal to x over log x up to a multiplicative constant which is close to 1. Another way of looking at this is that you may want to choose an integer at random between 1 and x, and the probability that this integer is a prime number is roughly 1 over log x. All right, so there are several refinements of this theorem, actually lots of them. But if you want to go further, so approximate better this function, you want to consider this logarithmic integral. Function. This function Li is the integral from 2 to infinity of, let me double check. Log of x. And so it has the same asymptotics as x over log x. So we could replace here egg log x by the logarithmic integral, and we have the same statement, but you can go slightly further. Right, so for example, sorry, yes, thank you. Thanks. All right, so one of the refinements is the following. So there is some constant a, so that the prime counting function is equal to the logarithmic integral plus some horrible error that doesn't really matter, but I just want to write it to make a point later. So some error that crucially is smaller than the logarithmic integral. Okay, so that's the main point. So this is O x over exponential. Okay, something. It's not that important. Perhaps what's more relevant here is the fact that the difference between the logarithmic integral and this function, egg log x, is asymptotically bigger than the error, which means that you cannot replace the logarithmic integral here by the function x over log x. So you need somehow the logarithmic integral is a better approximation of the prime counting function. So that's what you want. And right, so you may ask now, so what would be the best situation? And this is essentially wide open, so I think there are some improvements on this quantity, but they mainly focus on making this implicit constant as small as they can. And they usually want something that is valid for every value of x, so you have a better approximation for a given number pi of x, sure. However, to the best of my knowledge, there hasn't been any dramatic improvements on the error term, on the asymptotics. So for example, let me just state here as a question, which is, I think, wide open, so it's there. An epsilon, so that the error term is, so you have some power savings. The question is open, but there are some results. So we know, and this is the point I want to make, is that these type of error estimates are closely connected to the locations of the zeros of the Riemann zeta function. So that's what I want to emphasize here. So in particular, there is this theorem by von Koch, 1901, that says basically, so suppose there is some epsilon between 0 and 1/2, so that the Riemann zeta function so the assumption is that the Riemann zeta function does not have zeros of real part bigger than 1 minus epsilon. And the conclusion is that we have then similar estimate. You get some log term, but essentially you get a power savings error term of epsilon. So in other words, if you have a zero-free strip for the Riemann zeta function, this translates directly into a power savings error term in the prime number theorem. Yeah, sure. I think there was a conjecture that it was always of the same sign, and they found an example of the order of 10 to the 32 or something. Yeah. So it does oscillate, but to pick up the oscillation, you have to look at really, really large numbers. Yeah. OK, so there is this connection between the location of the zeros of the zeta function and the error estimates on the error term in the prime number theorem. That's the point. And this is actually goes back and forth. So the prime number theorem, you could say, is equivalent to the statement that there are no zeros real parts. OK, so it's not completely true, of course. Well, they're both true statements, so they're equivalent, right? But OK, there is this elementary proof of the prime number theorem that doesn't even use the Riemann zeta function at all. But OK, whatever. But that's basically the, at least if you follow this analytic approach, that's the moral of the story. And this can be essentially be reversed, and getting a power savings of epsilon is in fact equivalent to have a zero-free strip so no zeros of real parts. All right. OK, so that's all I wanted to mention about prime numbers. Oh, right, of course, the conjecture here, so the Riemann hypothesis is that we do have this for 1/2, and that would lead to an error term of square root of x, roughly. All right, so I would like to discuss this very beautiful result by O and Winter that where they have a similar asymptotics for periodic points of rational maps. So now the idea is that you want to order the periodic points of a given rational map according to size of the multiplier, for example. And you want to count the number of periodic points that are less than or equal than a given cutoff. And the theorem of O and Winter is that for uniformly hyperbolic maps, you have a very similar type of estimate. OK, so let me introduce some notation. So let's suppose we have a complex rational map. And P, some periodic point. I want to introduce some notation. So pi of P will be the minimal period. P hat will be the orbit. So maybe to be precise here, it's formed by all iterates up to the minimal period minus 1. So it's a set of pi of P points. And we want to introduce this number, lambda of P, that measures. So we are going to use this to measure a periodic point, the size of a periodic point. This is the norm of the multiplier of P. Okay. Now, for the theorem, it's more natural to consider orbits instead of periodic points, so I'll also introduce, say, the minimal period of the orbit itself, and then the size of the orbit. And we want to consider what would be the analog of the prime numbers, so the set of all periodic orbits. And right, so we want the counting function, so the number of periodic points that are less than or equal periodic orbits, which are less than or equal than x. There's several, right? So like 4. What do you mean?
Well, there's pi, which is the period, and then there's pi, which is the counting function.
Yes, capital pi, it's large pi. Let me. Okay. It's capital pi. Okay. All right, so any other question? Okay, so the theorem is one winter. It's the following. We take some, suppose that f is uniformly hyperbolic. And it's not conjugate to monomial. Say, in the quadratic family, we don't want to take c squared. And the theorem is that there is an epsilon so that the prime counting function has the asymptotics of as in the prime number theorem. And I forgot to define delta. So delta here is the Hausdorff dimension of the Julia set. All right, so, okay, I mean, you can maybe do some computations to see that this is the right expected number. I mean, you would expect that to have roughly x to the delta, and this goes, gives a more precise, way more precise statement. So, and the proof relies, before talking about the proof, let me mention briefly some of the story. So there's a long list of results here. Let me mention a few. So this more or less started with I wouldn't say you would go, say, all the way up to half delta. We would, I think we do expect to have some zeros, these so-called resonances. And they would translate into having a other terms here. So basically, every zero would contribute with maybe a smaller term there. So what you could expect is that maybe, so in a good scenario, you might have like a definite epsilon and then perhaps a finite number of terms of this type. That's more or less. But Yeah, so I don't think, so even in the hyperbolic case, that sounds out of reach for now.
Just to make sure, do you expect like many zeros between delta and delta over 2?
I don't really know. Yeah, I don't have a sense really of what would happen. Yeah. All right. Okay, so this prime orbit, really the first result was by Haber in 1961, and that was for compact surfaces. Of constant negative curvature. And this does include, so the very first result does include the error term. He used some theorems of Selberg. Then this was extended by Sarnak to the finite area case. So crucially, it applies to the modular curve. And after a long time, yeah, geodesic flow. Yeah, thank you. So the geodesic flow, and we're counting closed geodesics so that are prime in the sense that you go over the geodesic exactly once. So you do the minimal period. Right, and then so finally, I mean, let's say, similar version to this was established by Polycott and Sharp. That's 98, and same, except that here we crucially have a variable. So Margulis proved in his PhD thesis in the 1970s that you had the prime number theorem, but without the error term. And it took a long time to establish the error term for variable curvature, which is somewhat closer to the hyperbolic case. And this is based crucially on this cancellation technique of Dolgopiat. That, yeah, so Dolgopiat introduced this for a different purpose, and Polycott and Sharp adapted this technique to for this prime to get the error term. All right, so the idea of this, the proof of this theorem is, roughly speaking, similar to this story here. So there is a Ruel zeta function that will play the role of the Riemann zeta function. And you can almost take von Koch's arguments and replicate them in the dynamical setting. This was done by Polycott and Sharp, but it's really close to the case of prime numbers. So perhaps, and we have the same heuristics here. So so this power savings in the error term comes from a zero-free strip for the Ruel zeta function. Okay, that's the upshot here. Okay, so this Ruel zeta function can be defined as follows. This is a product over all orbits of I mean, if you take the Euler product for the Riemann zeta function, you just replace the prime number by the size of the periodic orbit, then you have your, this is the Rho zeta function. And Rho proved several things about this. So for example, so in the uniformly hyperbolic case, first we have that this Rho zeta function converges and is non-zero on the right half plane where we have real part bigger than delta. Delta, again, is the Hausdorff dimension of the Julia set. So if we have the plane here, complex plane for the variable s, we have the Hausdorff dimension, delta, and Rho proved that you have convergence and no zeros on this right half plane. He also showed that there is a meromorphic extension to a neighborhood of delta, and there's a simple pole at delta. So it's very similar to the situation of the Riemann zeta function where we would replace delta by 1. You have a simple pole there too. All right, and somehow for this is an indication that somehow what's behind all of this is that Rho also shows that every zero of the Riemann zeta function, of the Rho zeta function, is in some sense a point in the spectrum of a certain transfer operator. Okay. Okay, so there is an interpretation of the zeros of the Rho zeta function, and that's somehow why we can do something about this, right? So basically avoid, all the game is to get estimates on these transfer operators to show that there are no eigenvalues. Right. Okay, so right. Okay, so basically the proof of this result by O and Winter is by showing that there's this zero free strip. So the heart of the work is showing that there is epsilon, so that the Rho zeta function has no zeros. Of real part bigger than delta minus epsilon. So by this classical argument from number theory, you get the error estimate following the approach by Polycott and Sharp. And again, so the key part is to use these Dolgopiat cancellation techniques to show the absence of eigenvalues and then the fact that there are no zeros. Okay, so so the idea is to go beyond the uniformly hyperbolic case and see whether you can establish some type of estimates of this type. Now, if you take some map that is far from being hyperbolic, say a Feigenbaum map. Sure.
Do we know, even when this, what class of maps guarantee that this counting function is finite? Is there sometimes for some x?
Yeah, so the Feigenbaum map gives an example where this is infinite. Now, whether you can.
But whether we have, is this no?
Well, I mean, I guess you need infinitely many, I mean, the multipliers to grow to infinity. How do you classify? Yeah. Sorry? Yeah, of course you are. Yes. yes. So that's the next, yeah.
Okay, sorry.
Right. Sorry?
What about stochastic quadratic real polynomials? Do they have a finite function?
Stochastic in the sense of.
Absolutely continuous and whatever.
Yeah, that's interesting. I would say maybe not. They're not. So you have these long parabolic cascades that you can, this long branch map that sometimes they're called, and I believe they can have infinitely many points. Yeah, of bounded multiplier. Mm-hmm. Yeah, so basically for the Feigenbaum, quadratic map, this is basically infinite. So for large x, and the reason is that if you take, so the renormalizations of this map converge in C1 topology, so the, say, alpha fixed points of the nth renormalization will have a multiplier that converges to some limit, and you just take any x that is bigger than that limit, you'll get infinitely many periodic points. Right. Okay, so basically the upshot is that it's perhaps difficult to go beyond Cole-Ekman. So I want to argue now that how the Cole-Ekman condition appears naturally here. And you can do that by analyzing the convergence properties of the Royal set of functions. So here we have this formula. But yeah, so this is like for the Riemann set of function, you have two formulas, one which is this Euler product, but you also have the usual power series that gives you all the analytic properties. So similarly, you have a formula for the real set of function that is more, it's better to analyze the analytic properties of this function. It's more difficult to write. It's the exponential of a series. So oof. All right, so basically here, we are summing over n, and the main contribution here is the sum over all periodic points of the weight raised to the power minus s. Okay, So if we want to use the root test to look at the convergence of this function, you want to look at this number. So something like
So you've got an absolute value here, put that over there. I'm just trying to compare this. You've got an absolute value of a multiplier here.
yeah, lambda comes with a multiplier. Yeah. Yes.
I'm
Yeah.
just wondering, I mean, you don't have one over there. Is it supposed to be one over on the other side?
Lambda includes an absolute value, and I do want an absolute value here too.
Okay, just like, because you have an explicit absolute value over there, so I was just wondering whether.
Oh yes, sorry. Yeah, no, that's okay. Yeah, thank you. All right, so basically you want to analyze the asymptotic behavior of this number, and we can just bound this by the real part of S. Yeah. So can define then the limit of this asymptotic growth. Yeah. And this is precisely one of the manifestations of the geometric pressure function. Which is just what it is, this limit. And we know a lot about this function. But so what we really want here for convergence is that to have values of t where this number is negative, right? So this number being negative means that we have some nice bounded limit that would translate into the real set of function converging and not having zeros in that area. Now, turns out that if you have a map that does not satisfy this Collegman condition, then this function is non-negative everywhere. Okay, so at least it will take you more work to show convergence. Okay. Okay, so let me say that F is TCE, topological Collegman, if there is lambda naught, so that for every periodic orbit, the multiplier has norm at least lambda naught to the n. So you have an exponential growth of multipliers in terms of the period. Here, period. And this is an old theorem by Chitsky, Smirnov, and myself. Says that the following, so there is a dichotomy. So either, so if F is TCE, then the set, so this is a Bowen type statement. So this geometric pressure function is negative precisely on the ray from the house of dimension to infinity. So it behaves like the hyperbolic setting where we would have convergence on the right half plane starting with the real part delta, so bigger than delta. And the second one is that if f is not TC, then in fact this is non-negative everywhere. So this is for every t. Okay, there's one problem I want to mention here that has bothered me at least for a long time. So it may happen, I don't know how to rule out. So I mean, if you follow all this interpretation of this function as a pressure function, you would expect this to vanish precisely at some point, hopefully some type of Hausdorff dimension, and then for this to be 0. However, we cannot rule out a situation where this function is strictly positive everywhere. Okay, we don't know that. Now the abstraction, so the situation that for this to happen would be that you would have an exponentially large, for certain times n, you would have an exponentially large number of periodic points of period n where the multiplier is exponentially close to 1. So if you had some type of Fatou-Shishikura, some quantitative version of the Fatou-Shishikura inequality, you might be able to rule this out, but I have no idea. We have some results saying that if the bad situation happens, so you don't have this Bowen type formula, then you not only would have this exponentially large number of periodic points that are exponentially close to being parabolic, but they would also be close together. They would be exponentially close to each other. So that's a very unlikely situation, and I just have no idea how to.
And you mean exponentially close to the number 1, not just an absolute value?
Exponentially close to 1, yeah. Exponentially close to 1, and they're exponentially close to each other. So that, I mean, the heuristic idea would be to do what Mitsu did for the Fatou inequality and try to perturb slightly and convert lots of them into parabolic points. But OK, I haven't managed to do anything like that. So yeah. Right, anyway, so here, so some indication that if you want to go beyond that, so TC is natural, so it's closer to the hyperbolic setting in that you have a result similar to REL, where you have convergence and to a non-zero function on the right plane with real part delta. And perhaps going beyond that might be a bit difficult. So for example, one case that would be interesting is this Fibonacci map. So if you have a unimodal map with the Fibonacci combinatorics, we know that for high order, you have this generalized renormalization, and it behaves like the Feigenbaum map, where you would have the prime orbit counting function will be infinite. However, for quadratic maps, there are these estimates by Miller and Lyubich that the multipliers do grow, not exponentially, but roughly, I think it's an exponential to the log of the period squared, maybe, if I remember correctly. That by in itself might not be sufficient, but in fact, in principle, I mean, we know so much about the dynamics that it might be possible to get some counting of the same type. Okay, but you know, it's like every Tuesday, I think is true for Fibonacci, and Thursday is, I think, is false, and then okay, so I don't know. All right. Okay, so right, so we started this with Shiqian Li. And so it's work in progress, but I think we can extend this theorem to the TCE case. Right. So same story. Okay, and that's not the last name of my co-author. That's the logarithmic integral. All right, so the issue, of course, here is that there might be critical points. So if there are no critical points in the Julia set, then you're back in the uniformly hyperbolic case. And you need to deal then with critical points. That's the major issue. And one way of doing that is using this inducing scheme. Oh, yes, thank you. All right, so there are many ways of going around this, but one is using this idea of nice sets. Where basically you want to so the idea of inducing is to accelerate the map. So the map is not uniformly hyperbolic, so you basically accelerate it. So you go do several iterates at once to pick up some uniform expansion. But you need to stop somewhere. And one way of doing it is to pick a neighborhood of the critical set. So we are looking here at critical points in the Julia set. And we want to consider then an induced map that would be essentially the original map, but where we go a bit faster at certain places. You define a certain domain, the good points. Yeah, so B here is the union of these neighborhoods of the critical set inside the Julia set. And you have some domain, so the good points. And you have an induced map. So this is some return map that may not be the first return map. It might, in general, it's going to be a higher return map that goes from this domain to B. And basically, what you want to do is to consider a nice set here. So, and this is some type of Markov or puzzle piece where it has this Markovian property, but going for backwards. Basically, if you take a pullback connected component of some iteration of B, then you're either completely inside or disjoint from this nice set. So you have this type of Markov partition. This helps you to define a map that would take each connected component of the domain univalently into one of these components, so you have some type of iterated function system. Okay? So that's perhaps the better, so it's almost like an iterated function system. And of course, there is a price you pay for reducing to this hyperbolic map. So this map is uniformly hyperbolic. And so roughly speaking, first, there will be some periodic points that will never get close to critical points, and there's no way you're going to count them. And there are periodic points that come close to the critical point, so they do enter this nice set, but they don't have a good return. And in those situations, you just lose the periodic point. So roughly, so one of the steps in the proof is the following. You consider the quotient between the Royal zeta function and the Royal zeta function of the induced map. And you can show that there are no zeros. So it has no zeros. Of real part bigger than delta minus epsilon. So there is epsilon, so that this is true. And the reason is basically the following. So you look at the points that never enter this nice set, and you have this type of Sierpinski carpet. So imagine that the Julia set is everything. And the points that never enter the nice set, it's some Sierpinski carpet. And in particular, it's some hyperbolic set, uniformly hyperbolic set. Now, the dimension of that set is smaller than delta, because you somehow removed an open set from the dynamics. And that allows you to control one part of the dynamics, and then there's a combinatorial argument to deal with the remaining ones. All right. So let me just finish by saying, so I'm running out of time. So with Chikian, we realized that there's a problem with this theory, right? So you have nice sets that don't have a nice boundary. Okay, that's a problem. And it's somehow crucial to implement this Dolgo-Piat cancellation technique to have a nice set that has a well-behaved boundary. So one of the steps in the proof is to show that, say, for a TCE map, there are arbitrarily small that are quasidisks. You can even quantify, so basically, you can get some dilatation constant arbitrarily close to 1, which means that in particular that these are roughly round, very close to a circle, and very small dilatation. Okay, so maybe I'll stop. So thank you for your attention.